Hi all, this is Abe from B351, and we're going to be working through an implementation of the A* search algorithm on the Tower of Hanoi problem in this video. I made this video with the help of ideas and slides from Peter, another one of our UIs. Just a small warning, in the interests of making the algorithm as clear as possible, this tutorial uses a different structure than the A3 assignment used this semester, fall 2018. Please use this video to help you understand the concepts, and be aware that you may have to apply the same concepts to a different programming framework on the homework assignment. The Tower of Hanoi is a puzzle made of 3 rods and discs of different sizes which slide down onto the rods. The puzzle starts with the discs stacked on the first rod from largest up to smallest. The goal is to move the stack of discs onto the last rod, following these rules. Only one disc can be moved at a time. Each move consists of taking the top disc from one of the stacks and placing it on top of another disc or on an empty rod. And no disc may be placed on top of a disc that is smaller than it. This puzzle can easily be represented by a search tree, with each state of the puzzle being a node, and each state having child nodes representing the moves that can be made from it. Now let's talk a little bit about heuristics. How can a computer understand which state it's in? Well, oftentimes it can benefit an algorithm to have a rough idea of how close a state is to the goal. This is accomplished through a function called a heuristic that maps states to real numbers. The heuristic value of any given state is an estimate of how much it will cost to get from that state to the goal. In this problem, an estimate of how many steps it will take to have the entire stack on the last peg. How useful a heuristic is depends on 3 things. The first is how accurate it is. How good is it at finding the closest states to the goal? The other 2 are special properties called admissibility and consistency. Admissible heuristics never overestimate the distance to the goal. I'll talk about why this is important when I explain the A* search algorithm in more detail. Consistent heuristics are a little trickier. The condition for a heuristic to be consistent is that for any node, and any successor of that node, the node will have an estimate less than or equal to the sum of the successor's estimate with the cost to go from the node to its successor. Importantly, when step costs are all 1, such as in the Tower of Hanoi or the sliding tile puzzle, this condition is equivalent to saying that the heuristic will never decrease by more than 1 from a point to its successor. The point of consistent heuristics is that they never hide good solutions by giving the first state in a good path a higher estimated final cost than a later state in that path would have. I'll talk about why this is important to the A* search algorithm later as well. Please note that all consistent heuristics are by definition admissible, but not all admissible heuristics are consistent. The A* algorithm is an informed search algorithm that begins at a start state and finds the path to the goal state with the smallest cost. Here, cost is the number of steps taken. We'll use this to find an optimal set of moves to solve the Tower of Hanoi puzzle. It does this by keeping track of the available states in a queue called the fringe, and expanding states according to some priority function, aiming to find the best path to the goal the fastest. In the standard A* implementation, the priority function is the estimated final cost, the cost of reaching a node, plus the estimated distance from that node to the goal. While the fringe is non-empty, the algorithm considers the node with the lowest ranking, checks that a better path to the node hasn't already been found, checks whether or not the node is the goal state, and then expands all of its children, calculating their costs, histories, and rankings. Its children are then added to the queue and sorted in according to their rankings. The algorithm continues until the goal node is expanded or until the queue is empty, meaning that there is no path to the goal node. Just because I'm a math major, I'm going to throw in a proof here. If the heuristic is admissible, then the first time that the goal node is expanded will always be the best path to the goal. That's because if there is any node with a better path to the goal, then its actual final cost, the cost to reach it plus its actual distance to the goal, will be lower than the cost of the potential path to the goal. And since the heuristic is admissible, then the estimated distance will be lower than the actual distance, resulting in an estimated final cost that is lower than the actual final cost, which is lower than the cost of the potential goal node. So the optimal path of the goal will always be expanded before any other possible path to the goal node. Now, if the heuristic is consistent, then the first time that any given node, not just the goal, is expanded will always be the fastest path to that node. I won't get into the proof for that here, but please feel free to look it up or ask Saul about it. The result is that you can keep track of the explored states as a set rather than a dictionary. In my implementation, just to be explicit, I do keep track of the explored states as a dictionary. The A-star algorithm is quite similar to the uniform cost search and greedy best first search algorithms. Each of these uses different priority functions to decide the order in which to expand nodes. I'll talk more about these during the programming portion of this tutorial. Before we get to the programming portion of this tutorial, though, I just wanted to quickly tell you a little bit about Python's heap queue module. Priority queues are abstract data structures where each element has a priority associated with it, and we use these in order to always get the node with the lowest ranking for our A-star algorithm. A priority queue is a list that is sorted in a very specific way, not unlike a tournament bracket from tennis or basketball. The module heap queue has two functions, heap pop and heap push, that add and take items from this queue, maintaining the special sorting mechanism. Heap pop removes and returns the element with the lowest priority from the queue, and resorts the elements so that they are in the correct order. Heap push adds an element to the list, and then sorts the list in order to maintain the priority of the elements. In the Fall 2018 Assignment 3, the state class implements the __less than __ self other property function to compare its own f value with another state's f value property. What that basically means is that each state represents its own priority using this less than function. However, our implementation here simply stores each node as a tuple with priority first, which sorts as we desire. Now let's get to the code. To find the successors of each state, we first make a list of the top disks for each peg. Then we consider each top disk and look for pegs with larger top disks. Those are the pegs we are allowed to move the disk onto. We then yield each of these moves. Because our problem has exactly one goal, we are able to create a heuristic based on the observation that certain discrete and well-ordered stages must be passed through in order to reach the goal. The number of such stages left to complete makes an estimation for how long it will take to reach the goal. This sort of heuristic can be called a stages heuristic, and while it is not always the most accurate heuristic, it has the advantage of always being both admissible and consistent. It is admissible because each stage takes at least one step to complete, meaning that you will never have a case where there are more stages left than there are steps left. And it is consistent because you will never jump more than one stage per step. The heuristic will never jump by a quantity of more than one. In the Tower of Hanoi problem, these stages are the steps of disassembling the stack of disks on the first peg, and the steps of assembling the disks on the last peg. Note that a certain step will necessarily be moving the largest disk directly from the first peg to the last peg. Care must be taken to count this as just one stage. I check which stage we are at by finding the size of the uninterrupted sequence of disks from largest to smallest on the first peg. One of these disks will be removed during each stage. If the size of the stack on the first peg is non-zero, I subtract one from it to account for the single step where the largest disk is moved directly from the first peg to the last peg. And then finding the size of the uninterrupted sequence of disks from largest to smallest on the last peg, one of these disks will be added during each of the later stages. Then, The number of stages left, and thus the value of our heuristic, is the number of disks left to remove from the first peg, plus the number of disks left to add to the last peg. Don't worry if this was all a little bit difficult to understand. As long as you can verify that this heuristic is admissible and consistent, that is what matters. Now we implement our 3 priority functions. Uniform cost search sorts states according to the cost of reaching them. Greedy, or best first search, according to their estimated closeness to the goal. And A* search according to their estimated final cost, the cost of reaching them plus the estimated closeness to the goal. Finally, we implement the search algorithm. First, let's just make sure that if the user doesn't specify a priority function, we just use the standard A* function. Now, we're going to store items in the fringe as tuples of ranking, state, cost, path. We'll start by calculating each of these for the start node, then creating a fringe that contains its tuple. We also create an empty dictionary to represent states we've already considered and their costs. Now, whenever there are still states for us to expand, we pop the lowest ranked tuple and keep track of its state, cost, and path. We check whether or not that state had already been explored, and if it has been reached by a lower path before, we continue, not considering it further. If this is the shortest path to the state, then we add it to explored. Next, we check whether or not the state we are expanding is the goal. If it is, then we return the path that we took to reach it. Finally, we iterate over the state's children, calculating the cost, path, and ranking of each, and adding each one's tuple to the fringe. If the while loop terminates, then we have exhausted the fringe. That means that there is no possible path from the start node to the goal, so we return none. And that is all you need to have a good implementation of a search algorithm. I'd like to just emphasize that the code for the A* function is definitely the most important part of this assignment, and it's that part that I hope that you'll definitely understand. The rest of it is rather particular to this problem. I hope that you have enjoyed this video. If you have any sorts of questions at all, please feel free to come to our office hours, write us on Piazza, or see Saul directly. Best of luck to you as you work on the A3 assignment.